SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be starting the transient response specification. Before we proceed to the specification part, we need to highlight why we have to consider the under-damped system practically for implementing the control system design. Then we'll give the expression of the step response of the PD control system, from which we'll be deriving the specification part. Then we'll conclude the lecture with the definition of the different specification which we'll be using to improve the transient response of the control system. Then we'll conclude the lecture. Hello everyone, this is the lecture number 17. We'll continue from the last lecture on the transient response specifications. In the last lecture, we came up with 3 different conditions on damping ratio. When the damping ratio lies between 0 and 1, this is basically under-damped response. When it is equal to 1, critically damped response, and when the damping ratio is greater than 1, over-damped response. But for aircraft application, generally we consider the damping ratio lies between 0 and 1. This is the condition generally we use for aircraft control system. Now, I'd like to highlight why we have to consider the damping ratio in this range. Let me highlight a few important points. If you consider these conditions, it was first. Let me highlight first point. Faster response. Under them, systems more quickly to change in input or disturbances compared to overdamped or critically damped system. This faster response can be crucial in situations where rapid adjustment are necessary for stability or performance. This is the one reason why you have to consider the underdamped system. Second, improve handling characteristic. So under this, let me write an underdamped response can contribute to better handling quality characteristic. making the aircraft more responsive to pilot inputs, more responsive to pilot inputs. This is particularly important for agile and maneuverable aircrafts. This is also very important point. Why you have to assume the damping ratio in that range. Third point, reduced settling time. We'll discuss what is the settling time. We'll discuss very soon. Under this, under damp systems tend to settle to the final value more quickly than overdamped systems. This characteristic also desirable in applications where minimizing settling time is a priority. Fourth point, enhanced sensitivity to control inputs. Underdamped systems exhibit oscillatory behavior. This is already we've discussed how it is oscillated behavior arises for the underdamped system behavior in their response. These oscillations can enhance the sensitivity of the control system to small inputs. It's a very, very important point. So if you use this kind of system, it will be the sensitivity of the control system to small input will be increased, enhanced, allowing final or finer control and tip point we can write stability margins. The underdamped system system's response can provide better stability margin. In certain situations, making the system less prone to instability So these are the points why you have to consider the damping ratio should be in this range. But it is depends also in some situation made sense, but most of the cases we generally consider the damping ratio in this range. Also, there are another point can be the control authority because if you want to consider damping ratio higher, so there will be control authority will be huge, requirement will be increased because to provide that kind of damping to the system, you should have that kind of control power in the system. That is another reason maybe. Okay, let's go back to our the dynamic system, what you have considered before. So we had the transfer function. Okay, well, now on you will consider the damping ratio in between 0 and 1 under damped system. Under damped systems. So based on the above points, we are going to consider the damping ratio should be in this range. Now, the transfer function we had ys upon rs equal to omega n square divided s square plus 2 zeta omega ns plus omega n square. So as we discussed that will be considered the step command in the system. So we'll assume R of t equal to 1, a step command. And we'll see how the response going to be for this step command. And if you take the Laplace transform, R of s equal to 1 upon s. And for this Rs, the step response, why it is step? Because the command is 1 by s, step command. The step response is given by y of s omega n square s square plus 2 zeta omega ns plus omega n square into 1 upon s. And now if you use the partial fraction approach, we can expand y of s in a partial fraction y of s equal to 1 upon s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. Further, we can extend this term equal to, we can write 1 upon s minus s plus zeta omega n divided by s square 2 zeta omega n s plus omega n square minus zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. So we can expand this expression, this form. Now let's compute the denominator part in this term and in this term, we can expand that term again, s square. So we are trying to simplify this expression so that we can apply the inverse Laplace transform and we can get a nice form. S square plus 2 zeta omega n s plus omega n square equal to, we can write s square plus 2 zeta omega n s plus zeta square omega n square plus omega n square minus zeta square omega n square. We can write in this form, and from this we can further write s plus zeta omega n square plus omega n, we can take common square 1 minus zeta square. And from this we can write further, this is, we know we already had omega d equal to, for the underdamped system, we had omega n root over 1 minus zeta square. That is the expression we had. So if we take omega d square, we can write omega n square into 1 minus zeta square. So in place of this, we'll substitute omega d square, s plus zeta omega n square plus omega d square. Now, if you substitute this expression in equation number, let me write this equation number 1. Substituting the above expression, the above in equation 1 yields, we can write y of s equal to 1 upon s minus s plus zeta omega n divided by s plus zeta omega n square plus omega d square omega d square and minus zeta omega n by omega d s plus zeta omega n yes omega n square plus omega d square. So we have multiply omega d here in both sides, in the denominator and numerator, to make the things in more simplified form. And taking inverse Laplace transform, taking the inverse Laplace transform yields, get y of t equal to minus 1 minus e to the power minus zeta omega n t cos omega d t plus, we can take minus common, so it will be plus. So zeta omega n divided by omega d sine omega d. So this is the expression. This is the expression for step response in time domain. So here basically we have used the Laplace transform of e to the power minus at sine omega t. If we take Laplace transform, we have omega divided by s plus a square plus omega square. And if we have e to the power minus at cos omega t, if we take Laplace transform, we can get s plus a, s plus a square plus omega square. So if you take the inverse Laplace transform, you'll get this expression. So these are the terms we have used in the equation number 2. This is the equation number 2, and equation number 1. Now we have our step response of the second order system, and on this system we'll be defining the specification. What are the specification will come up? Let me define what are these specification, then we'll find those the expression of those specifications. Based on the, let me write, based on the unit step response. Why it is unit step? Because we have taken r of t equal to 1 unit step. This is the expression we have taken. That is our unit step. Unit step response a number of different specifications may be given as the first specification we are going to derive is rise time, which is denoted by TR. Let me define what is this. The time taken for the step response to first reach the final value. In a response plot, will be showing how it look like, how we'll find this rise time. Just after some time, we'll be showing this. Another specification, peak time, TP. The time taken to first achieve the peak value or the peak response. And specification we have maximum overshoot. We did it by MP. The maximum percentage overshoot from the final value. Fourth specification will have settling time, TS. The time taken for the output to get within 2% of the final value. We'll assume 2%. Maybe some cases there are different system, different percentage used, but we'll be 2% final value and stay there. Now we'll see how this specification can be seen in the response plot. Let me go to new figure. Let's assume we have a response, this time axis, and the step response y of t. And since we are assuming step command, so we are having the final value my aircraft should maintain this final value. For example, let me write y final. Okay, this is y final. And the response I'm having, starting from here, this goes like this, and it is something like this. Now, as for the definition, first let's go to rise time. The time taken for the response to first reach the final value. So here, this is our final value. So this is the response, this is the response plot, and it first reaches to the final value here. So this is the, we can denote this time taken from this to this is we can denote by TR. And the second is peak time, the time taken to first achieve the peak response. So this is our peak response here, the maximum peak. So time takes to reach to this peak, we can denote as TP, peak time. And now let's move to the maximum overshoot. The maximum percentage overshoot from the final value. So in this case, this is our maximum overshoot from the final value. So we can denote this is MP. Now the settling time, the time taken for the output to get within 2% of the final value. So we can say, if you assume this is the value, let's assume this is 2% from the final value. This is the response and this is the final value. And between these 2% error is there. So once the system reaches to this value, we can say, so this is the value we get. At this time, the time takes to reach this value, we can denote this is TS. So this is how we can define the specification for a response. Now, as a control engineer, the control system will modify this specification so that you can fulfill your mission objective if you want to fulfill your mission objective very quickly, then we have to modify the TS settling time. Or if you want to have less overshoot, less oscillation in the system, so we have to work on the maximum overshoot, how we can modify it. Or if you want to reach the final value very fast, so that we have to modify TR. So how the controls algorithm should be designed so that you can modify this response and you can get the better response, better objective. So this is how we'll be designing the control system. Let's stop it here. We'll continue from the next lecture and how we'll be coming up the expression of this specification using these definitions. Thank you.